In my previous videos on graphs and graph theory, we've only really considered definitions and notations and such for graphs. But the application of graphs and graph theory is huge, and it is such a growing field of mathematics, especially over the last kind of a few decades. So what we're going to look at in this video is just going to have a look at some different modelling applications that we have with graph theory. So we're going to have a look at a couple of famous problems first of all. So the first problem is the Königsberg Bridge problem. So what we've got here is we've got 7 bridges, we've got 2 islands, and then we have 2 land masses either side of a river in this layout. You can start wherever you want, top either island or on the bottom. Are you able to walk across every bridge exactly once? You cannot swim, you cannot fly, you must only get from land to land via the bridges. But you can start wherever you want and you can finish wherever you want. If you want to pause the video and have a go, see if you can solve that problem. If you had a go at that problem, you might have found that there are indeed no solutions. You cannot start anywhere and cross every bridge exactly once. You have to duplicate a bridge if you want to cross every bridge. This is a famous mathematical problem, and we can summarize its situation using graph theory. So what I'm going to do is I'm going to mark each landmass with a node. So I've got a landmass at the top, the 2 islands and 1 at the bottom. So I've got 4 nodes. 1, 2, let's lay it out the same as that actually. 1, 2, 3, 4, there we go. So I've got the 2 land masses either side of the river and then the 2 islands. And then each bridge is going to be represented as an arc. So from this top landmass to this island, I've got 2 bridges. From this to that island, I've got 1 bridge. And then 2 from that to the bottom. And then 1 from that one to the bottom. And then 1 between the 2. If I just colour in the nodes just to make it clearer where my graph is. This graph now represents exactly that problem listed above. So I'll be able to start on any node and move across every arc exactly once without repeating any arcs. And I've always said the answer is no. You don't actually study an algorithm to do this on this course. Not modelling with algorithms, but it is an interesting problem all the same. What I'm doing here is I'm just jotting down the degrees of the nodes. So just a reminder from the previous video, the degree of a node is how many arcs attached to it. So there's 3 arcs on this one, 3 on this one, 3 on this one, and 5 on this one. When you're doing a journey around a graph, then if you enter a node, you must leave a node, like such. If I enter a node, I must leave a node. Which means as I walk through a node, I'm taking up 2 of the degrees. So if I reduce that by 2, I get 1. If I reduce that by 2, I get 1. I can reduce that by 2 twice, leaves me with 1, and leaves me with 1. I'm left with 1 everywhere. I can't. There's no way that I can start somewhere and finish anywhere, having crossed every bridge exactly once. And I would need either 2 odd ordered nodes or no odd ordered nodes. I cannot have 4 odd ordered nodes such as what I had here. So yeah, that's the Königsberg Bridge problem. Another famous one is this one. This is called the utilities problem. Imagine we've got 3 houses. I've numbered them 1, 2, and 3. And then I've got 3 utilities. I've got electricity, water, and gas. And what we want to do is we want to supply each of these houses with each of these utilities. So we're going to get a bipartite graph because we're not going to join houses to houses, and we're not going to join utilities to utilities. So we've got 2 groups of nodes. Each house is a node and each utility is a node. Is there a way to connect each house to each utility such that none of the arcs cross? So you can't have any arcs crossing. So again, if you want to pause the video, try and have a go at this. Okay, if you had a go at it, what you should have found is that no, it is not possible. You can get 8 of them down, but you're not going to be able to get the 9th one in. So let's just illustrate that. If I put one arc there, one arc there, and one arc there, so all of the houses now have electric. To get water, I can join that straight to 3. I can't get to 2 that way. I have to go all the way around 3 to get to 2. And I can get to 1 by going this way. And then when I come to do the gas, we can see that house 3 is inside this cycle. So I can't get to house 3. I can get to houses 1 and 2. Okay, there's house 2 for gas. There's house 1 for gas. But I can't get to house 3 because it's trapped between these 2 electric arcs and these 2 water arcs. So that's the utilities problem. And in fact, even if I extend this piece of paper to infinity in every direction, it's still not possible. You still cannot join all of the utilities to all of the houses. If you wanted to kind of picture that differently, if I put all 6 of these icons on a sphere, I still wouldn't be able to join up the 3 utilities to the 3 houses without intersecting. Again, very off topic, but an interesting point nonetheless. If you put these 6 icons on a different shape, it may be possible. So for example, a torus, which is a donut, that's a kind of sphere that's had a hole punched through it. It is possible to join them all up because you can loop this one round on one of the rings to join it up to house 3. So it's not possible on a planar space, but it is possible on other spaces. But yeah, interesting problem nonetheless. Okay, let's have a look at some questions. All right, we've got 4 people. I've called them A, B, C, and D. And then to be assigned to one of 4 jobs, which I've called W, X, Y, and Z. Each person must be allocated to 1 job, and each job needs to be carried out by only 1 person. All right, so we've got some information now about each of the people. Person A can do jobs W and X. Person B can do jobs X and Z. Person C can do jobs W, Y, and Z. And person D can only do job Z. Okay. So we're going to draw a bipartite graph, which represents which jobs the people can do, and then we are going to assign the people to 1 job each. So it's bipartite because I'm going to have 4 people on one side of my graph. So I've got A, B, C, and D, and on the other side I've got the 4 jobs, which were W, X, Y, and Z. I'm just going to fill those in again, just so we can see clearly that these are nodes. And it's bipartite because a person doesn't connect to a person and a job doesn't connect to a job. It has to be something from the left-hand group connecting to something in the right-hand group. Okay, so this bipartite graph is going to represent which jobs people can do. So A can do W and X. So that would be those 2 arcs. So now the arcs are representing not so something physical like water pipes or electric lines, but they're now representing something abstract, in this case, which jobs can be done by which person. B can do jobs X and Z, so I'm going to draw a line from B to X and from B to Z. C can do W, Y, and Z, so W, Y, and Z. And D can only do job Z. So I'm going to go across that way. Okay, so there's my bipartite graph. That answers the first part of the question. The second part of the question, assign the people to 1 job each. Okay, so clearly I'm going to be choosing 4 arcs if there is a solution, because I'm going to choose 1 job per person. 1 person goes to 1 job. So it makes sense to start at person D because they can only do Z. So that means I'm choosing this arc, which then rejects this arc because I can't have C doing Z and B doing Z because D is doing Z. That means then that I am choosing this arc because B has to do a job. And then because B is doing X, we don't want A to do X. And then that leaves A has to do job W. Like so, I'm choosing that one, which means that C then can't do W because A is doing it, which leaves C to do Y. So there's actually only one solution to this problem, and that is A does job W, B does job X, C does job Y, and D does job Z. All right, next question. This graph shows routes between settlements in Cornwall. Okay, so we've got Penzance, St Ives, Redruth, Truro, Falmouth, Newquay, St Austell, and Bodmin. Part I of the question, explain why this is a graph. Okay, so nice simple answer. Okay, don't forget we are using graph theory from decision maths. So this is a graph because it contains arcs and nodes. Don't forget there are other words that you could use. Okay, arcs could be interchanged with edges and nodes could be interchanged with vertices. Okay, it just contains arcs and nodes. Okay. Part 2, describe 2 possible routes from Penzance to St Austell. Okay, so using these specific arcs, we've got we can go from Penzance to Redruth, and then we can choose to go either up to Bodmin and down to St Austell or through Truro. Okay, so there's my 2 routes. So to draw out those 2 routes, or to answer the problem, I'm going to say Penzance, and then we're going to go to Redruth, and then we're going to go to Bodmin, and then we're going to go to Truro. Sorry, St Austell. Whereas the alternative route was, again, starting in Penzance, we're going to go to Redruth again. In fact, you have to go to Redruth from Penzance, according to this map. Then we're going to go to Truro rather than Bodmin. And then we're going to go to St Austell. Okay. So there you go. You've got 2 routes from Penzance to St Austell. And laying it out like that is absolutely fine. You've got node and then an arrow then to another node. And this represents a route that you are taking, or a path that you are taking. Okay, and then on to one of the most famous graphs in the world. It has had some flourishes added to it to make it different looking from what this graph perhaps looks like, but I'm sure that you will recognise it. There we go. This is a graph of the centre of London, specifically the underground trains. So this is still a graph. The nodes are the stations. So we have bigger nodes where lines cross, and we have smaller nodes, still a node on this graph. This would be classed as one node. And then all the arcs are train lines between stations. But what's different about this graph compared to all the other graphs we've seen is that there's been extra information that is displayed on this graph compared to the other graphs. So the different coloured arcs, they represent different train lines, and some of the nodes have got little disabled symbols in, which tell us about some of the access for disabled people at these stations. There's also some other symbols like this one, which tells us there is a Network Rail station there as well, so you can get overground trains. We've got some boat symbols as well for boat taxis for the Thames. There's a bus link. There's all sorts of extra information on this, but it is still a graph. It's just got extra kind of flourishes, if you like, to it to present more information. Okay, so let's say that we are at Waterloo Station. We can use this graph to decide the best way to get to, let's say, I don't know, let's say to Paddington. Okay, so at Waterloo, we want to get to Paddington up here. So we could ask, okay, well, how can we do that with the fewest changes? Well, let's look at all of these train lines that go through both of them. We've got grey, black and brown, and then this greeny colour over here at Waterloo, and then we've got yellow, green, pink and brown over here at Paddington. Notice that brown is common to both of them. So if we get the brown line, which is the Bakerloo line, from Waterloo, we're going to be doing 1, 2, 3, 4, 5, 6, 7, 8, 9 stops to get to Paddington. Okay. Now, is there a better way that uses less stops? Well, we could get the Northern Line train, 1, 2, 3, 4, change onto the Elizabeth Line, and then that goes straight to Paddington. So that is only 5 train stations away, but does involve a change of train. So this we can use this graph to plan routes around the centre of London. Another important kind of point to point out about this map and a lot of other similar maps around the world is this is not topologically, this is not geographically accurate. These stations are not necessarily this distance apart relative to each other in real life, because that's not the importance that this map is portraying. The important points that this map is portraying are how the stations are connected from one to another. We are looking at something that is topologically equivalent, or if you like, isomorphic to the true train lines. Okay, the train lines in reality don't go, oh, straight up, let's go 45 degrees up there and then straight up again. It's a bit more higgledy-piggledy, but that's not important information for this map, because this map is used for route planning. So there you go, a real life application of an isomorphic graph that hopefully you are all familiar with. Thank you very much for watching. That finishes my series on graphs, and next up we'll be looking and delving into networks.